Welcome to Live Sound for small to medium-sized venues. This is a four-part video series, and this is video one, which will cover background and general information. The four-part video series is broken out into this module, Module 1, which is background and general overview. Module 2 is sound distribution. This is speaker systems, how you distribute the sound out to the listeners with the front of house system and to the performers with the monitor system. Part 3 is sound capture. How do you get sound into the system? Microphones and direct boxes. And then part 4 is all of the electronics, mixing, board, effects, power amplifiers, all of those sorts of things. So just to define what we're talking about, a small venue, in my view, is up to about 150 people. A pretty modest sound system can handle that. Medium-sized venue is 150 people to about 500 people. Now you need a larger scale, much more powerful sound system. When you get above 500 people, a lot of this equipment we're going to talk about, you could push to 1,000 or so. I've even done like 2,500 people at a fairground, but it was more background music than anything else. If you start to get up towards 1,000 people or more, now you're talking about some different equipment. You're talking about, you really want vertical array speakers, and that's not something that I'm going to talk about in this series, and it's actually not something I've ever really worked with. Now, these principles we're going to talk about, they apply to larger venues. A lot of this basic information, it's just that the equipment required, particularly in the speaker systems, will be different. So who's this designed for? Well, sort of I want to satisfy three audiences. First of all, if you're a sound person doing sound, selecting equipment, setting it up, running a sound system, certainly this video series is for you. But secondly, in my experience, and I've been doing this for over 40 years, artists who perform through artists perform through a sound system. If you're an artist and you're successful at all, you're going to be performing through a sound system. There are things about how to do that well that a lot of artists don't seem to know, and I think would be very useful to discuss, particularly in Module 3, when we talk about capturing sound. We'll talk about how to sing into a microphone. We'll talk about your guitar, if you play acoustic guitar, and selecting a pickup and how important that is. And then if you run a venue, you own a venue, it's good to have an understanding of this stuff. So why listen to me? Well, I've done live sound since the mid-'80s. At one point in the 80s, I was doing 2 to 4 gigs a week, 48 to 50 weeks a year. So, a lot of experience, 130, 140, 150 gigs a year. Last several years, I've done sound for 2 or sometimes 3 stages at the Falcon Ridge Folk Festival. I was one of the sound people for the B&D Coffee House, although I haven't done that the last couple of years. But like at Falcon Ridge, I do sound for the Thursday night music stage on Thursday. I do sound for the workshop stage and usually the Slambovians dance set on Friday, and then Saturday and Sunday I do the workshop stage. And this is, all day. This is, 2 or 3 bands at a time getting on the stage and then swapping out to another 2 or 3 bands. So lots of changeovers, lots of experience with different things. I have really taken it upon myself to study this, right? I've read books, I've read articles, watched videos, and I've worked with lots of other sound people. I have a technical background. I have a degree in physics. I worked in technical positions in the computer chip industry actually for 45 years now. And I've worked with all genres, lots of folk, acoustic, Americana kind of stuff, but I've also worked with rock and roll, some hard rock and roll, jazz, lots of different things, and indoor and outdoor. And like I said, I did do about 2,500 people in a fairground once, and I've done 600 or 700 people. Well, I've 1,600 people a bunch of times, and 600 or 700 people. So quite a bit of experience. Um, this might sound obvious, but there's a couple of points to be made here. So the objective of a sound system is to capture an artist's performance and distribute it to the audience so that a larger audience can enjoy the performance. If you think about this, if you have a singer-songwriter and they're playing acoustic guitar and they're singing, a dozen or 2 dozen people can, kind of gather around them and hear them. But even then, you can run into a situation, and I've seen this quite a bit. Like you'll have an artist and they strum and they sing, and there's a pretty good balance. And then they start finger picking and they're singing at the same volume they were singing when they were strumming, and now you can't hear the guitar. So having a sound person capturing the guitar and the vocals separately and being able to fix that is very, very useful. But the other point here is the artist is the one doing the performance. The job of a sound person and a sound system is to capture that performance and accurately distribute it out to the crowd. Unless the artist says to you, oh, I want this weird effect on my voice, or I want you to make me echo here, or something like that, your job is to accurately capture and distribute what they're doing, right? You're not, you're serving, you're doing a very important function, but you're serving the artist and distributing their performance. It's not your job to be part of the performance really, or to change the performance. So there's 4 elements to a live sound system. So the first one is capture. You've got to get the sound into the system. So you've got microphones and you have direct boxes. So, if you have keyboards or a lot of, bass guitar or acoustic guitars with pickups, you run that into direct boxes to get the right impedance matching and get it into the system. For other things like vocals, for drums, things like that, you'll use microphones to pick it up. Part 2 is processing. So, you've got all these channels that you're capturing, and they all come into the mix board. And in the mix board, you're going to mix it. You're going to balance the different inputs to get a good, overall sound. You want to make it so that you can hear all the different elements that are performing on the stage at once. You might do some equalization. You might do some compression. You might do some reverb, some effects on these channels. So that's the processing piece. The output of this is the capture puts out a very, very low signal. One of the first things the mix board does is amplifies that signal, and then it does all this processing. But the output of the mix board is still a pretty low signal. So now you're going to amplify it, and you're going to take this signal, which has a relatively low amplitude, and you're going to increase it to have a very large amplitude, so you can then feed it into the speakers. Now, sometimes amplification is built into the speakers if you have active speakers. Sometimes it's separate. But either way, there's an amplification part, and then there's distribution, which is the speakers that distribute it out to the listeners, be it the people that are coming to the show that are listening through the front of house system, or be it the monitor system for the artists so they can hear themselves. Now, I don't want to, as much as I'm a physicist and I like to understand all this stuff, I don't want to deep dive into ridiculous levels of technology. But there's something I think is very important to understand. So there's, those elements I just talked about. There's 2 types of elements within that. Okay, there's an electrical element where you have an electrical signal that comes in and an electrical signal that comes out. If you look at a power amplifier where you're just feeding into it a low level from your mix board and you're turning it into a large level to feed into your speakers, people will argue with this. People will say, oh, I can hear difference between those amplifiers. Lots of people claim that. If you actually do a truly scientific experiment where they don't know what they're listening to, where they're just listening and use something called an ABX comparator, and basically you're listening to a speaker, and it's behind a curtain, so you don't know which one you're listening to, and then you press a button, and there's a second speaker, and it might or might not switch to the second speaker, or might not switch to the second amplifier. You don't know, only the computer knows, and it keeps track. And all you have to do is every time you press a button, you say, the sound changed, the sound didn't change, the sound changed, the sound didn't change. If you have power amplifiers and you're doing that test, nobody can hear the difference. There's like no statistical difference between what people think they hear. And this was done as a big experiment with all of these audiophiles that were supposed to have super good ears, and nobody could hear the difference. Now, that doesn't mean no electrical equipment has different sounds to it. A preamplifier interacts with a microphone, and there is some difference in sound to that. When you look at an equalizer, you're taking your sound and you're deliberately changing it, and how equalizers deliberately change the sound is different equalizer to equalizer. Compressors work differently, reverbs work differently. So this is not to say that electrical equipment doesn't ever have a sound to it, but in general, if you take an equalizer and you set everything flat, whatever you put in, you're going to get out, and you can't hear the difference. Like the electrical equipment is so good in terms of its deliberate fidelity in to out that unless you're deliberately doing something, it really doesn't have a sound to it. This is in contrast to electromechanical components. Okay, electrical mechanical components, you put an electrical signal in, and a mechanical component creates sound, or you put a sound in and a mechanical component generates an electrical signal out. For example, a speaker, you put an electrical signal in, you have this moving diaphragm in the speaker. There's like a big electromagnet, and a signal is being used to move that speaker, and that's making sound that's then going out to the audience or to the artist. Electromechanical systems, the sound in versus the sound out, have significant differences. Microphones, the same thing. A microphone, vibrations in the air vibrate a diaphragm, which then converts it to an electrical signal coming out. The point here being that speakers and microphones have a lot of character to them. They all sound different, much more so than electrical components. Okay, and this leads into the next slide, which is what determines how a sound system sounds. The most important element in how a sound system sounds is the speakers, for two reasons. Number one, they're an electromechanical component. Different speakers sound different, and people with reasonable training, even without training, can often hear significant differences between different speakers. And everything in the sound system goes through them, right? The speaker system feeding out to the front of house, every single thing you do is going through those speakers. And in fact, you as a sound person sitting at a mixer out in the audience are hearing what's coming out of those speakers, right? That is the single most important factor in the sound of the sound system. And kind of 1A is that the room and the speakers interact. And when we talk about sound distribution and we talk about speakers, we'll talk about how to place speakers, because you put a speaker on the floor, it accentuates the bass. You put a speaker in the corner, it accentuates the bass. You have a room with hard reflective surfaces, a lot of your mids and highs are going to just bounce off that wall, and maybe you want to aim the speakers so they're not hitting the wall so much. There's a whole bunch of things to this. Number two is microphones. Again, they're electromechanical components. They have a sound to them, very much so. Different microphones sound different, very different, and particularly when you start picking microphones for different instruments, there's huge differences. Or even for vocals, there's huge differences. You want to make sure you have the right microphone for the job. But microphones only pick up one thing at a time, and some things might come through direct boxes. So, microphones have as much character to them as speakers, but they don't affect the entire, everything all at once the way speakers do. So they're number two. And number three, a distant third, is the electronics. Now, I'm going to talk about some basic fundamental stuff here, and I'm going to try not to, get too deep into this, but there is some stuff you really should understand. So sound is vibration that travels through the air. It also can travel through solids, it can travel through liquids, but if you're standing at a show listening to sound, you're hearing the sound through the air. Sound has a frequency, which is how fast it is vibrating, and this is measured in cycles per second, otherwise known as hertz. So when people talk about, oh, that's a 20 hertz sound, that means that it's vibrating at 20 cycles a second. Lower frequency is low pitch, bass. So 20 hertz is like the lowest bass note a human being can hear. It's a very, very low sound. High frequency is high pitch, right? Think of the shimmer of cymbals. That's really, really high frequency. Sound also has amplitude, which is how loud is the sound. The higher the amplitude, the louder it is. And sound has phase. And we'll talk about this a little bit, how the sound waves line up. Phase differences can increase or decrease amplitude. Sounds can add together or subtract from each other depending on phase. So we'll go through all of these. It's just good stuff to understand for overall understanding of what we're talking about. So let's start with frequency. So the head of a drum is stretched tight. You strike the head, it'll move down and then up through the neutral point where it started, and then move up. So you hit this thing and the head moves down, it comes up through the neutral point, up to its maximum excursion, goes down, and over time it's dying out, right? So each down, neutral point, up, back to the neutral point is a cycle. So this is a cycle from here to here, this is a cycle from here to here, right, each time. Over time, the cycle dies out. So the amplitude in this figure here, the amplitude is going down over time, but you'll notice the distance from here to here, that's a cycle. The difference from here to here, which is a cycle, from here to here, that's not changing. So the frequency is the same, but it's dying out, which is the amplitude. So frequency is how many cycles per second a sound wave completes. This is called hertz. And in the figure below, so here's 3 cycles per second, which is 3 hertz. Here's 6 cycles per second, or 6 hertz. Here's 12 cycles per second, or 12 hertz. Okay, so as you're going through more cycles per second, you're going up and up and up in frequency in hertz. Now these are all extremely low. A 3 hertz note, you can't hear it. 6 hertz or even 12 hertz notes, you might feel that, but you're certainly not going to hear it. So the range of human hearing is generally agreed to be 20 hertz on the low end to 20,000 hertz. Now, this is also known as kilohertz because a kilo is 1,000. And you'll hear people say, oh, 20 to 20K. They mean 20 hertz to 20,000 or 20 kilohertz. Practically speaking, there isn't much music below 40 hertz. And most people don't hear much above 16 kilohertz. So get that range right, and you'll be doing your job well. In most small to medium-sized settings, if you're trying to get your sound system so it produces, sound down to 20 hertz really well, you're going to have enormous speakers, and you're going to be carrying around these gigantic things, and they're really not going to be doing much for you. I have speakers that go down to 40 hertz. My subwoofers go down to 40 hertz. I can pick one up in each hand and walk with them. And I have, with 4 of those in a high school gymnasium, had absolutely pounding bass, the floor moving, and everybody dancing like crazy. Like, you can do your job really, really, really well at 40 hertz. The thing is, most bass notes are only like 40 hertz, 50 hertz and above. Kick drum, the thump of a kick drum is about 50 hertz and above. There really isn't much below that. So, focus in this range, get this range right. Most adults are struggling to hear 16 kilohertz. They certainly don't hear 20. Maybe some kids do. So sound frequency from 20 to 40 hertz, very little musical content, and you feel it more than you hear it. You don't really hear it. 40 to 80 hertz, this is really important. So 41 hertz is the lowest bass note. The thump of a bass, the kick drum, they live here. And even this, you'll feel this. This will sort of move the walls, rattle the floor. this is this is where bass becomes really important. 80 to 160 hertz, low end of instruments, vocals above 100 hertz. There's a lot going on in this range. Most vocalists struggle to get down below 100 hertz. Some bass singers can get down maybe 75 hertz, a little lower, but generally that's about the limit. 160 to 320 hertz, again, low end of instruments, crowded range, all through here. 80 to 160, 160 to 320. And you'll notice each time I'm doubling, 20 to 40, then 40 to 80, then 80 to 160. We're doubling, we're doubling, we're doubling. 320 to 640. Boxy or money sound. If this is turned up too much, and by the way, there's lots of equalizers, like a 10-band graphic equalizer will generally be centered in each one of these ranges. So if you go, oh, my sound is boxy and muddy sounding, you use your equalizer and you bring this down a little bit and you get a better sound. 640 to 1.28 kilohertz or 1280 hertz. Honky, boxy, nasally vocals if too much. Okay, 1280 hertz, 1.28 kilohertz to 2560 hertz or 2.56 kilohertz. Moves the song forward or back. This is vocal presence. Okay, there are a lot of vocal mics. For example, the Shure SM58 vocal mic, which is like one of the most used vocal mics ever, one of the most famous vocal mics ever, has a bit of a peak here because this lets you cut through the mix. It really gives presence to your vocals, but too much of it at the high end, you're going to wear people's ears out. It's kind of fatiguing. 2.56 kilohertz to 5.12 kilohertz, gives a sort of edginess, brightness to the sound. If you don't have enough here, it's dull, but again, you don't want too much. And then, 5.12 to 10.24 kilohertz. So 10,240 hertz, 5,120 hertz. Brilliance, presence. Add a little bit of this to make vocals less dark and stand out. Again, don't want to add too much. And then 10,240 hertz, 20,440 hertz. Air, brilliance. But there's something called de-essing. So if people are really sibilant, they're like S sounds like sibilants. This sort of 5,000 hertz and above is where you're going to be, you might want to cut a little bit if somebody's voice is too sibilant. So instruments and vocal ranges. So this is the fundamental range, and these are the harmonics. So harmonics are sort of overtones that the instrument can produce. So cymbals, fundamentally are in the 300 to 1200 hertz range, but their harmonics can go all the way up to 20,000 hertz. Kick drum lives in the 40 to 630 hertz range, but again has harmonics even as much as 10,000 hertz, although not really very much up there. Snare drums, 100 to 400 hertz with harmonics up to 12,500. Toms are in the 80 to 630 range with harmonics up to 8,000. Acoustic guitar, 80 to 1600 hertz with harmonics up to 6300. The interesting thing is, as you start to get into all this, like here's a male voice, generally 80 to 1000 hertz with harmonics up to 10,000 hertz. If you put a microphone on a male singer and that microphone picks up things below 80 hertz, all it's going to be is noise from something else that you don't want in the channel. And anything above 10,000 hertz is going to be noise from something else that you don't want in the channel. Female voices are more like 300 hertz up to, and can be up to 20,000 hertz, although not much. But all of these things, you really want, and we'll talk about this a lot when we get to the capture section, talk about microphones. You want to make sure that you're capturing these ranges, and you really don't want to capture anything outside of these ranges. because anything you do, you know, and I'll get into this. I'll talk about this a lot more in the capture section. My philosophy is I want one and only one thing in every channel, and that's because that allows me to control the mix. It allows me to control the mix easily. When I push a slider up, I don't want the vocals to get louder and a whole bunch of other stuff to get louder. I just want the vocalist that's on that microphone to get louder. So I want microphones that are tailored to pick up the right things and the right frequencies, which is why microphones used on stages are generally very different than microphones used in studios. In studios, you have a very quiet environment. You want a microphone that picks every subtlety possible up, but on a stage, you have tremendous amount of noise. Right? Have somebody playing drums, that's leaking all over the stage. You want, you know, and you don't want that to be coming through the vocal mics any more than it has to, so that you can control the vocals without also bringing the drums up every time you change a vocal. So, you know, it's important to sort of understand this, to you know, pick microphones and really make sure you're capturing what you want to capture and not other things. And there are some resources on this page here down the bottom, scottandjones.com production. There's actually an equalization sheet that goes through a lot of this stuff. Okay, so sound levels. How loud is something? What's the amplitude of the signal? And so basically, this is done as a log scale, which is kind of a weird and confusing thing. But basically, every 10 dB is a doubling of the loudness. So 0 dB is the threshold of hearing. 10 dB is like breathing. This is, you know, this is twice the level of the threshold of hearing. A whisper is twice as loud as breathing. You know, a normal conversation is about 60 decibels. Okay. You know, 70 is a noisy restaurant, 80 is a vacuum cleaner, 90 is a hairdryer, 100 is a helicopter. You know, 100 decibels is really, really loud. And, you know, the interesting thing here is, so, you know, power saw or mower, siren, loud bar band. A loud bar band could be 120 decibels, right? That's incredibly loud. And we'll talk about this in a minute. It's actually really dangerous to your hearing. 130 decibels is a jet engine. 140 is the threshold of pain, front row at a rock concert. Okay, firecracker, shotgun blast. The loudest possible sound is 190 decibels. And I've kind of color coded this. So, you know, green is like, yeah, you can be in this forever, never going to bother your hearing. This is kind of okay. As you get in here, if you spend too much time in here, that can be a problem. And then this becomes really problematic. And by the way, so there's this company, Audio Tools. I bought their Studio 6 digital app, which I have on my iPhone and my iPad. And you can buy additional modules in it, and you can measure sound pressure level with it. So this is great. Like when I'm doing a concert, I'll usually have my iPhone sitting there running the sound meter all the time so that I can just look at it and see how loud I'm mixing. And then I'll also use some of the analysis tools on it, maybe on my iPad, sitting next to it for doing other things. This is a really nice this is a really nice program. A lot of other companies make similar kinds of things. I use that one. I like that one. They're not paying me any money or anything. So here's a sound wave moving through, you know, vibrating through space. So at increase in amplitude, you're basically increasing the height of this wave. So a 2x increase in height is a 10 dB increase. You're doubling the sound. You're doubling the height. It's 10 decibels. So safety. So safe hearing depends on the duration as well as the level. Okay, and these guidelines here are based on NIOSH, and basically, and this is the National Institute of Occupational Safety. These are sort of levels that you can, you know, sort of stay under these levels and work your whole career, and your chances of having hearing loss is pretty small. You know, and what you see here is 82 dB is okay for 16 hours. 85 dB is good for 8 hours. So like when I'm mixing, I usually try to mix in the mid 80s. I'm usually mixing for 4 to 6 hours. I might go a little bit higher, but you can sort of safely live in this zone. And most people coming in to listen are only going to be there for a few hours. So this is okay. But you start to get up here, um, and if you start to get up to 97 decibels, you start to get close to 100 decibels. It's only safe for half an hour. Most people can stay in there longer than that. Many concerts are over 100 decibels. I can't tell you how many times I've been sitting at a concert and pulled out my phone and measured the levels, and it's been 100, 110 decibels. That's damaging your hearing in a single concert, like in minutes. Um, so if I go to concerts now, I wear earplugs. Now you can buy foam earplugs. You can buy a bucket of them at like CVS for $10 or something, but they don't sound very good. They're muffled. They're cutting off the highs. Anemonic Research is a company that I really like. They make earplugs that are, pretty good. They're still a little muffled. The best option I've ever seen, I had Music Cares was an event I was at, and if you were a music professional, they would make earplugs for you for free, and they're custom fit. And these are basically, they pretty much sound like you turned the volume down. So if you're really going to do this, this is a great option. I even wear them sometimes when I'm mixing, if I'm in a situation where I cannot control the volume to what I would like it to be. And I'll take them in and out and check things and stuff, but you can mix a little bit with them in. And you say, well, wait a minute, you're running the mix board. Why can't you just set the volume you want? I've done lots of gigs in small rooms with drum kits where the drummer is just bashing away in a drum set, and the whole band has to come up to match him, or you wouldn't be able to hear the vocals and you wouldn't be able to hear the other instruments, and it's just really loud, and there's nothing you can do about it. You can ask the drummer to play softer, but good luck with that. And I've done a lot of work in these at music festivals in these metal buildings, and if you've got a drummer that hits hard up on the stage, it's going to be loud in there, and there's kind of nothing you can do about it. Now here's the other thing. So sound levels fall off approximately 6 dB every time you double the distance. So I did some calculations here just to sort of show this. So if your objective is under 100 decibels for safety, and kind of over 63 decibels or so, or below 90, below 90 for safe listening, but above like 63 decibels so they can hear the music. So here's a speaker at a distance of 1 meter, which is 3.28 feet. And you turn that speaker up so it's 80 decibels at 1 meter. This is going to be safe to listen to from 1 meters and out to about 4 meters. People are still going to be able to hear the music fine. Now, that's only 13 feet. So you say, well, that doesn't do the job very well. If you crank it up to 90 decibels at 1 meter, it's a little too loud at 1 meter. But if you make sure nobody's closer than 1 meter, if everybody's like 5 feet from the speaker or something, they're going to be in this range. And from 5 feet all the way out to 52 feet, from 5 feet to 52, 53 feet, you have sound that's in the zone that you want. Now, if you have to reach farther than that, now you crank it up to 100 decibels at a meter from the speaker. You want to make sure nobody's closer than maybe 10 feet to the speaker. That's not really that, it's not really that hard. Just sort of make sure everybody's about 10 feet back from the speaker, a little bit more, 12, 13 feet from the speaker. Here's 13 feet, it's 88 decibels. And now, all the way out to 210 feet, you have acceptable sound level. So, as you crank your speaker up, it projects farther and farther and further out to really, 130 decibels coming out of your speaker. It's going to be pretty loud, at 3,000 feet away. So I mean, if you need to project back fairly far, you just want to make sure that people are back from your speaker a little bit so that they're safe. And then, 100 dB at 1 meter, keep your listeners between 4 meters and 64 meters from the speaker. So that's 13 feet out to 210 feet. It's going to be fine. So you can cover a really long distance with, this is just speakers up on a stage. Some of these, these new vertical array speakers, they have a whole array of dozens of speakers, and they aim them all over the place, and they're able to control the sound in ways that you can't with just these single point source speakers. So there's a special kind of noise called pink noise, and it has equal energy in each octave. So when we talked about 20 hertz to 40 hertz, that's an octave. It's a doubling of frequency. 40 to 80 is an octave. 80 to 160 is an octave. It has equal energy in every octave. So if you feed pink noise into a speaker, and then you measure the output of the speaker versus frequency, right, you can see a curve. You can also do this on microphones, electronic components with special equipment. And on the next slide, I'll show you a plot of frequency. You want to do this over the range that you're using it for. So speakers, 40 hertz to 20,000 hertz or even 16,000 hertz is good. For microphones, it depends on what you're trying to capture. But here's an example. So this is a well-regarded vocal mic. And you see here, it's falling off down here. It really doesn't pick anything up, in these lower frequencies. But that's fine because, vocalists, even men don't produce anything below like 80 hertz, basically. So none of this matters. And you see here, it's very flat. And then it kind of climbs through here. And the reason it does this, and this is deliberate, this here is presence. This is cutting through the mix. This is your vocals being very intelligible. This is, nice, bright, good vocals. And then it rolls off out here, but who cares? Because there's not really any vocals up there, and most people can't hear up here anyway. So this is a microphone that will do a good job on vocals. It's not dead flat. And actually, when we talk about speakers, we'll talk about this too. You can measure the quality of a speaker to some extent by looking at how flat it is on one of these plots, but you actually, in practice, when you're using it, you don't want it to be flat. You want it to actually have a little bit of a slope to it. And we'll talk about that when we get to it. But now, one thing to keep in mind, though, it's got this peak here, right? It means it picks up sound the best at this frequency, which also means this is the frequency it's going to be most likely to feed back. So if you have a feedback problem, you might use an equalizer to notch this out a little bit. So you can learn a lot from these kind of plots. All right, now we're going to talk about phase, which is probably the most confusing part of this whole thing. Here's two waves moving through space near each other. They are both in phase. This one's going up and then down, and this one is going up and then down in sync with this. They will add together and give you this. These two waves of a certain volume will create a new wave when they interact of double the volume. Here are two waves interacting. This one's going up, this one's going down, this one's going up, this one's going down. They're exactly 180 degrees out of phase. They're exactly mismatched to each other. These two will actually interact with each other and you will get nothing. So phase of waves that, if your sound waves are in phase, they will add together, you'll get constructive interference. And if they're out of phase, you'll get destructive interference. And if they're exactly out of phase, you can get no sound at all. Now, complex musical signals interference can increase or decrease the amplitude of individual frequencies, resulting in complex interference. So what happens here is, you have to be careful about things like microphone placements and things like that. Like if you're miking your drums and all your mics are on top of the drums, that's probably okay. But sometimes in order to mic something, you might put the mic under the drum so that the person playing the drum isn't hitting the microphone with their stick or something. Like I've mic'd a snare drum from the bottom many times. Um, if you mic it from the bottom, the signal for the snare drum coming out of that microphone will now be out of phase with all the other microphones for the drums, and you can get some destructive interference. Now, there's a simple fix to this because most mix boards have a switch where you can press a button and it puts the signal 180 degrees out of phase. So if you say, oh, okay, I'm going to put this microphone under the snare drum, you just press that button and it fixes it so that you don't have the interference. But this plays into exactly how you place microphones, how you place speakers, and we'll discuss this more later. But that's just the basic concept. And it is, it's kind of a weird concept, I know. So in this video, we went over the basic background information needed to put the next 3 videos in context. Part 2, we will discuss sound distribution speaker systems, how to use them for front of house and monitoring. So resources, our production page has a resource section with presentations. These presentations, not only are these videos available on my YouTube channel, but on our production page here, scottandjones.com production, these presentations are up there so you can just download the presentation and look at it. And also there are some other reference materials available, like there's an equalization sheet that goes through, has a lot of information on one sheet about different frequencies and instruments and how that all works, and there's a whole bunch of other things. Thank you for your attention. I hope you found this useful.